Hello everyone, today we'll be discussing exact equations, and exact equations are just particular types of differential equations that are of this particular form. So we say a differential equation of the form m times dx plus n dy equals 0 is exact if there exists a function, two variable function f of x comma y, such that the partial of f with respect to x, f sub x, or partial f with respect to x, however you like to say it better, I prefer this method, this notation better though, is equal to m, and partial of f with respect to y is equal to n. Now in this case we say that f of x comma y equals c, some arbitrary constant, is the implicit solution to the equation. So we're trying to find some function, f of x comma y, so two variables, such that its partial with x is the function attached to dx, and whose derivative with respect to y is the function attached to dy. Good. Now again, once we found that function, then we can just say that function equals c is our implicit solution. If we have a initial value problem where you have an initial condition, I should say, then you can actually solve for c specifically by plugging in specific values for x and y, of course. But if not, then you can possibly just solve for y in terms of x, or worst case scenario, if you can't, just leave it like this, depending on what f of x comma y is, of course. Now to check if such an equation is exact, we can actually just verify that the partial of m with respect to y is equal to the partial of n with respect to x. Now why does this work? Well, here's why it works. If m, let me just write it off to the side here, if m is equal to f sub x and n is equal to f sub y, then notice my must be f of, well, f sub x sub y, the second partial derivative, if you will, and similarly n sub x must be f of y sub x. Now there's some detail I'm leaving out, of course. If f is continuous over its domain, then or wherever it's differentiable, then these two are actually the same. So if these two are indeed the same, then it must be true that if m sub y is equal to n sub x, the partial derivative of m with respect to y is equal to partial of n with respect to x, then it must follow that that m is a function with respect to x, and n is that derivative function of that same function with respect to y. So it's basically because of this in reverse. Now there are some things that I'm leaving out, some details, small details, where this doesn't necessarily hold all the time, but for the most part it will, especially with the problems we'll be seeing, some basic simple examples. Now in the next screen I'm going to try my best to real quickly, hopefully, explain why this is kind of true, and it'll kind of get a little bit into calculus 3 if we've seen those ideas before involving vector fields. But then after that we'll jump into an example where we'll actually see all of this in play. Alright, so here again I just want to justify a little bit what I discussed previously. Now given a level curve, so-called level curve, f of x comma y equals some constant c, imagine that this kind of black curve I drew here represents some surface in three-dimensional space, which is the surface of the graph of f of x comma y in three-dimensional space. And let's take a plane, z equals c, and take a cross-sectional image of that surface. So that's what I'm drawing here in red. So let's imagine when we actually look at that on the xy plane, or its shadow on the xy plane anyways, this is essentially the graph of f of x comma y equals c. Good. So what you'll notice is that it's one complete finite loop. So with that being said, you can take a line integral over that region. And if you don't recall, one of the big results from calculus 3 was that if you take a line integral along a curve c, so here I guess we can call this c, but since we're already using c, let's call it something like gamma. So if we take a line integral along the curve gamma of f of x, specifically not of f of x comma y, but of the gradient of f dot dr, where r is the vector that explains the trajectory of the point along gamma, which again, that's a little detailed, but this ends up being 0 because it's a closed loop basically. Right. Well, not just because it's a closed loop, but because what does the gradient of f represent? It represents derivatives. So this is essentially true because of the fundamental theorem of calculus, but the fact that gamma is a closed loop, the endpoints of the curve end up being coincident, they end up being the same. So you get f, the original f of the endpoints, subtracted from each other, but they're the same, so we end up getting 0 as a result. So it's a little detailed, but I have actually a video on that if you want to look at that. That's the fundamental theorem of line integrals, if you're curious. But now look, if we kind of expand out what this is the vector whose components are f sub x, f sub y, and dr is just, well, I guess you could think of that as the vector whose components are dr sub x, comma dr sub y. Well, maybe that's not the best way of putting it. Maybe we can write it like this, dx comma dy. I guess that works a little better. I still don't like that too much, but that's not too bad actually. Because look, now if we have this, if we take the dot product of this, then we'll have fx dx plus fy dy. And this looks very much like what I had from the previous screen. We called this m dx plus n dy. And this is supposedly 0. Now, of course, this isn't an integral, and this doesn't quite explain what the details of what we had previously, but this gives motivation. And in fact, this gives enough motivation where we can kind of start here and kind of consider writing something in this form. So instead, we have this, and this gives motivation for that. But instead, what happens if we take the derivative of this with respect to x on both sides? Well, of course, the constant sign will give you 0. Similarly, if you take derivative with respect to y on both sides, you'll also get 0. And how can we combine these in some way that makes sense? Well, of course, if we just multiply by dx here, we just get that. And if we multiply by dy here, we get something pretty similar. And then finally, combining these together, we get fx dx plus fy dy is equal to 0 indeed, telling me that f of x comma y equals c is a solution to this differential equation. So going backwards naturally will give us a nice result. Now, I've justified it enough where I'm confident in saying, yeah, that's kind of more or less why it's true. But now, how do we actually go about solving such an equation? That we'll have to see in an example. But essentially what we'll do is we'll take the antiderivative of m with respect to x. We'll get plus a constant, but in fact that constant could be in terms of y, as we'll see due to partial derivatives and the way those behave, which we need to have a refresh on as well. But from there we can take derivative of that result with respect to y, partial of that with respect to y. I'm kind of saying a lot without doing it, so let's take a look at that example right now and see what that entails. Alright, so here we have these two examples that look fairly different, so let's take a look to see what they're about. By the way, notice that they are indeed of the form m dx plus n dy equals 0 for each of them. We have some crazy function in terms of x and y, which are m multiplied by dx, added to another crazy function involving x and y, which we call n times dy, and that's equal to 0. So that's clearly the case for each of these. There is no initial value or initial condition in these problems, so these are not initial value problems. But anyways, we'll try our best to verify that they're indeed exact. For the first one, it's a quick check. Derivative of this with respect to y, so m sub y. Of course, this is our m and that's our n, that's fine. Derivative of this with respect to y is going to be 6xy squared. Derivative of this with respect to x, that's going to be 6x y squared, and that derivative is 0. So let me just kind of touch up on what I've done here. So to take the partial derivative of a function with respect to x, you're treating y as a constant. So I'm looking at, well, here we're actually taking derivative with respect to y. So now we're treating x as a constant though. So x is kind of ignored, it's just a constant. So think of what is the derivative of y cubed? Of course, it's 3y squared by power rule. Multiply that to the constant 2x, we get 6xy squared. Derivative of this with respect to x, since y is a constant, this term is a constant on its own whose derivative is 0 completely. So that term is gone. Derivative of 3x squared is 6x times the constant y squared gives us 6x y squared. These are the same, so that's a quick check that this ought to be exact. Perfect. Now, how do we actually find the solutions m and n? Well, not m and n, but how do we find the solution f of x comma y whose partial derivatives of f end up being m and n? Well, here's what we do. we're going to look at m, so maybe now is a good time for me to do this labeling. I was kind of waiting on that. So let's call this m, of course. Let's call this n, as we've seen just now. And now let's just go for it. So we want m to be f sub x, so that's the partial derivative with respect to x. So we're going to take the antiderivative with respect to x. So I'm going to call this ad sub x, if you will. Now, of course, we know what m is. M is 2xy cubed. Now, the antiderivative of 2x is x squared. So this is x squared y cubed plus some constant. Now, before I write the constant, let's verify. Derivative of this with respect to x. Well, derivative of x squared with respect to x is 2x times the constant y cubed. Indeed gives us this, 2xy cubed. But now that I'm going to write the constant, you expect me to write c possibly. But I'm not going to do that. I'm actually going to write some letter I haven't used yet. Let's use g of y. Because a function purely of y is a constant in the eyes of x. So the derivative of this with respect to x would be exactly this, because derivative of this term will end up being 0 because it's purely a constant in the eyes of x. Good. Now that we have that, we're going to take the derivative of this, not antiderivative, but now derivative, with respect to y. Because if this is our supposed solution f of x comma y, then this partial derivative with respect to y should be equal to n. Notice we want some function f of x comma y whose partial with respect to x is m, and whose partial with respect to y is n. So its derivative with respect to y should line up with this. Let's take a look. So derivative of this with respect to y, derivative of y cubed is 3y squared. So it's 3x squared y squared, because x squared is a constant multiple that comes down for free. Derivative of g is, let's just call it g prime of y. And derivative of, well, n itself, our supposed f sub y, is n itself, which is 3x squared y squared. So far so good, matches, that's good. Plus 6y to the fifth. So notice, these are the same, these must be the same by subtracting these out. Now we're golden, because we have this function in terms of y purely. So that makes sense. So now what we're going to do is we have this function in terms of y. We're going to take the antiderivative to get rid of the prime, basically. Antiderivative of 6y to the fifth is, of course, well, just y to the sixth. And you can see that because derivative of y to the sixth is 6y to the fifth. Basically, for anti-power rule, you add 1 to the power, you get 6, divide by the new power, the 6 is cancelled. Now we have plus some constant c, but here we just want to find some solution. We don't really care of writing plus c itself. The reason for that, you'll kind of see once we finish the problem in a second, but just know that we're not going to write plus c when we antiderive the, or take the antiderivative of the function purely in terms of one variable like we've just done here. But anyways, now we have somewhat of a solution. So our solution is the following. It's f of x comma y is equal to, well, it's this guy. X squared y cubed plus g of y. But now we know what g of y is. It's y to the sixth. And now again, you probably expect me to write plus c because this would be plus c. Well, here's where I don't, because remember, if you recall from what we saw previously, we just say f of x comma y equals c is a solution to this. So if I had written plus c, it would be plus c1 equals some other constant c2, subtract c1 to both sides, c2 minus c1 is just another constant, call it c. So long story short, you don't need to write plus c when you take the antiderivative in the last step. And this is indeed a solution. You can verify that this indeed checks out. So we verified it was exact using a quick verification. So that checks out. They're both the same, they're equal. Awesome. And then we actually saw the process now, how to find such a solution. Fantastic. Now notice, it may not always be the case you can completely solve for y in terms of x or vice versa. In this case, it's kind of possible, but it involves completing the square. It gets a little messy, so I'm not going to do that. I'll just leave it like this in so-called implicit form. Now, this one looks a little crazy, and it is, it's a little involved. Shall we take the derivatives? Let's see. So we know, of course, this is m and this is n. Let's see how crazy this is going to be. So what's this derivative with respect to y? Do I even want to do that? It sounds like a gross mess. I mean, this part's not too bad, but this part will involve product rule. And something I kind of want to say is that the verification step isn't necessary usually. It's not actually completely necessary, I should say. But it's nice to check, because if you try the verification process, the step here, and you verify that it is not exact, this is not satisfied, then there's no point in continuing. Just say that the equation is not exact. Doesn't mean there's no solution, but at least we verified that it's not exact. And that means you can't really proceed with the method. But if you just continue to proceed with the method, sometimes you'll see if you get a contradiction or not. Now, a contradiction would occur where you have, let's say, g prime of y is equal to something that's in terms of y and x, something like that. Now, that's possibly what could happen along the process, along the way. Now, again, if you take the derivative of this with respect to y, it's not too bad. Here you'll need product rule, so it's a little bit of a mess. But I think we'll get some cancellation. Let me just say that I verified already this is exact. Try it on your own for this verification, that m sub y is equal to n sub x. It should be a good practice for you. But it should work out in the end. What I'm going to do, though, is I'm going to attempt to just take the antiderivative of this with respect to x, because we want to get f. This is f sub x. This is f sub y. Now, if you look at that, that sounds like a mistake, because taking the antiderivative of this with respect to x seems like a little bit of a nightmare. We have two terms that involve x in both locations, here and here. Taking the antiderivative, that basically allows for by parts to sneak up on us, and I don't want to use by parts if we don't have to. So instead of doing this, I'll do this one first. This looks a lot simpler in regards to y. So the antiderivative of this with respect to y requires no product rule, because we only have y on the inside, not on the outside. Awesome. So let's take a look at that. So that means f of x comma y is equal to the antiderivative of this with respect to y. Antiderivative of cosine is positive sine. X cubed is a constant that comes off with free on the outside, and that's of x, y. Now the antiderivative of, derivative of xy with respect to y is just x, because you drop the x. You drop the y. Right? Derivative of y is 1, so derivative of xy is just x. So by chain rule, we need to divide by x. So long story short, we get x cubed over x, which is just x squared. Now you can verify this indeed works. Derivative of this with respect to y. Derivative of sine is cosine. By chain rule, derivative of the inside with respect to y is x. We gain a new x on the outside with cosine of xy. It's exactly that. But now we have plus a function, let's call it g, purely of x. Now taking the derivative of this with respect to x, by product rule here, we get derivative of the first times regular of the second, plus regular of the first, x squared, times derivative of the second, cosine of xy, but by chain rule, derivative of xy with respect to x, drop the x, you just get y, plus g prime of x. Now if we compare this to m, because remember we want this to be equal to m, I think it compares exactly. Notice, this term is equal to that term is equal to this term, we're golden. So g prime of x is then going to be set to 0, comparing term by term. Kind of like we did here when we actually saw that g prime of y had to be a new term that we didn't see ahead of time. But here, it's like there was no term because they match exactly. So if g prime is equal to 0, antiderivative of 0 is just a constant, but again, we don't write the constants at that step. So in fact, this will be our solution then. So in fact, let me just say that this f of x comma y, 2x sine of x comma y, x times y, not x comma y. There we go. Plus x squared y cosine of xy equals some constant c. That guy right there, that is our solution to this exact equation. Awesome. So that took a little bit of time, but they were pretty, I think, different examples, so that gave us a nice variety there. Now we're going to look at something a little different. I want to do an initial value problem, but I also want to take a look at a case where it doesn't appear to be exact, but there's a way to make it exact. So let's take a look at that right now. Right, this one seems a little crazy. Let's see what we can do. Now, we have this kind of weird setup first. Doesn't look like it's an exact equation type of problem, but I'll convince you that it is. And we also have an initial condition, which we haven't actually seen applied to these types of problems yet. So we'll see how that's handled. But again, we'll take care of initial conditions at the very end. Okay. So first we'll start solving like normal. Now the first thing I want to convince you of is that y prime is just a funny way of saying dy dx, which we have seen before. Okay, the next thing is that we can multiply through by dx. So we'll get the first term, which is our supposed m, multiplied by dx, plus 2y multiplied by dy, because the dx is cancelled in that term, equals 0. So we can see clearly this is an exact type of equation where that's m and that's n. But it doesn't work out, does it? No, not at all. Because derivative of this with respect to x is 0. Derivative of this with respect to y clearly is not 0. In fact, it's, derivative of the top is 2y, and then it's over this constant, x plus 1. And that's not equal to 0. So, as it turns out, yeah, this is not an exact equation, at face value anyways. What do I mean by that? Well, there may be a way we can multiply through by a factor. Notice multiplying through by some function will not affect this side because 0 times anything is 0 regardless. But it may make it so that these two m and n become a new function m and n each, such that it actually is exact. Now that also may not always be possible, so yeah, it's a little touchy, but let's take a look. I mean, I wouldn't be asking these types of questions if it wasn't possible anyways. So there's always hope, I guess you can say. So what can we do? Well, here's what I'm going to do. I'm going to write, let's call it u, and I want to multiply u to each of these. I'm going to multiply u to x squared plus y squared over x plus 1 dx plus, let's write it as 2uy, and then that's dy. And I want it to be so that, well, my is equal to nx. How can we make that the case? So we're kind of forcing our verification step. So our verification step again is m sub y is equal to n sub x. Here it didn't work. But now we have a new my, or new m and a new n. So now we want to verify that this works. Now the only thing is we don't know what u is. I made it seem like it's a constant, but u really is a function either of x or of y, or possibly both. But in this case, I'm going to say that it is a function of x only. Why do I want to do that? Well, I think it should maybe make things a little easier, but now that I'm looking at it, it looks like it's going to be a little bit of a mess to see. Actually, it won't be too bad, because notice if this is in terms of x, that won't affect this y. So derivative of this with respect to y should be still pretty easy to actually go with. So let's see. So this is our new m now, and this is our new n. And my is going to be, well, this is in terms of x only. So here I'm going to kind of, let's just assume that u is a function of x only. So u is equal to u of x, if you will. Okay? So with that being said, derivative of this with respect to y is just, this is a constant, so that's just u itself, multiplied by derivative of this with respect to y. Derivative of the top is just 2y with respect to y, over x plus y, of course, because dividing by a constant is the same as multiplying by a constant, so it doesn't affect the numerator, which we'll be taking derivative of. So that should be fine. Now, on the other hand, n sub x, well, now this is a function in x, so its derivative, we'll call it u prime, and then 2 and y are constant, so those come down for free. Good. Now we want these to be equal. We're going to force these to be equal. Forcing them to be equal gives us an equation now in u, which kind of like seems like we've created a new differential equation, which is kind of true, but we have the fact that u is purely in terms of x. So let's see what we can get going here. Well, we want them to be equal. So u, let me write it like this. So let's write it as 2uy over x plus 1 is equal to 2u prime y. And how can we solve this? Maybe this is like a separable equation, possibly. It's a little hard to tell. The good news, I think, is that u is in terms of x only, like I said. So we can possibly move all u's to one side. Yeah, I think that's a good idea. Let's do that. So notice we can just divide by 2 straight up. We can also divide by y straight up too, so that's nice. So we actually get, if we move things around, 1 over x plus 1 is equal to u prime over u. Now this is good because the antiderivative of u prime over u, if you don't recall from logarithmic differentiation, is just u itself. Well, it's ln of u itself. So now taking the antiderivative of each side of this with respect to x, so let me write dx and then dx, of course, we end up getting here, this is just ln absolute value of x plus 1. equals, here we'll have, absolute value of, ln of absolute value of u. And then of course plus a constant on each side, which I'll just write on one side. So let me just write here, we have ln of x plus 1, let's say plus c, is equal to ln of u. Now I may have gone a little crazy there. I mean, it's hard to verify that is indeed true, but I mean, after thinking about it for a bit, it shouldn't be too hard to figure that out. If you do a u substitution here, or a w substitution, something like that, if the bottom is equal to w, the derivative of w would be dw, well I guess it'd be du, which is u prime, would be du over dx, so that's just u prime. And then you end up getting this. The u prime over u is just 1 over w dw, whose, antiderivative is ln of that. So you kind of just get this anyways, which is kind of strange, but yeah. Or I guess another way of seeing it is that if you look at this as du over dx over u times dx, think of the dx's cancel because we have one in the denominator, one in the numerator. So this is really 1 over u du, whose antiderivative is ln of absolute value of u, and then up to adding a constant. So that's another way of seeing that, but from a logarithmic differentiation, if you ever have derivative over the original, then its antiderivative will always be ln of the denominator. Okay, good. So with that being said, can we solve for u now? Yeah, we'll just take both sides as powers of e, like this, here and here. These cancel, so now we get u in absolute value is equal to e to this plus c. We can write this as e to this times e to the c. Now remember that e to the c is a constant itself, so we can write this as some new constant, let's call it c again, times these cancel, and we get times the absolute value of x plus 1. So really what we have is u is equal to x plus 1, or a constant times x plus 1. But in fact, we'll just take it to be x plus 1, and let's see if it works. So, and again, we only want to find a factor that works. Here I'm kind of doing it in a way where we're finding a general factor, but we want to find only one factor. Here we're kind of given a family of factors, if you will, that work. But notice just dividing by c gives you something that works anyways. So u being x plus 1 should work. I'm going to erase this and we'll check that right now. So I've erased a few things here. We've gone back to what we had here. And we wanted u to be only a function of x. Let me talk real quickly about why that was the case to motivate that assumption. Normally for these kinds of problems where it's not exact but you want to make it exact, you want u to be purely in x or purely in y. There are some cases where that's not the case, but those are the easier cases to do, and that's all I'll be talking about really today. But specifically, if u is a function of y, that would make this differentiation with respect to y pretty bad, because we'll have to use product rule because you'll have y squared times a function of y. Here, it'll actually just be pretty simple though, because u times a function of y times a function of y, there we go, is purely in y, and its derivative in terms of x is just 0. So that's not good because we'll still have a similar problem. So that leads to all sorts of contradictions. Letting u be equal to a function of x, I think, is really the only choice here. Now, what we found out is that u equals x plus 1 is seemingly a pretty suitable solution. How can we verify this? Well, if we let this be equal to x plus 1, let me just kind of erase as we go along here. This is going to be 2 times x plus 1 times y, like that. And now we can verify, notice here, these cancel out straight up. So now we get something that looks a little different. We get x squared plus y squared all times dx. And then here if we distribute this, let's distribute both 2 and y. No, it looks messy, but that's fine. We get 2xy plus 2y dy. Now this is an entirely different looking exact equation, exact type looking equation, but it stems from the same thing. All we did is multiply by some non-zero factor, supposedly. I mean, it's only 0 when x is negative 1, but we're assuming that's not the case. Okay, good. Now what? Well, now is this exact? Well, what's the derivative of this with respect to y? That's going to be just 2y. And derivative of this with respect to x, that goes to 0 for that term. And here you drop the x, so you just get 2y as well. 2y is equal to 2y. We verify this is indeed exact. Antiderivative of this with respect to x is going to be 1/3 x cubed plus y squared x. Because a constant has antiderivative, that constant times the variable we're antideriving with respect to. So that's the antiderivative with respect to x. Taking the derivative with respect to y now, that goes to 0, okay? And let me just be sure I'm okay so far. This goes to 0 and this goes to 2xy, because derivative of y squared, of course, is 2y times x is 2xy, plus some constant in terms of y, which is a function of x. Let me make sure that's okay. Hang on. Kind of getting things mixed up here, aren't I? Here is where we write plus a constant, which is in terms of y. There we go. My mistake. So now we take antiderivative, not antiderivative, now we take derivative with respect to y. That goes to 0, that goes to 2xy, good. And then we have plus g prime of y, which is going to be the other term if you kind of compare these, which is just, of course, 2y. So if g prime of y is 2y, write that a little better, sorry. There we go. If g prime of y is 2y, then clearly g of y is the antiderivative of 2y, which is y squared. So that means this guy here is our solution. We have 1/3 x cubed plus y squared x plus g of y, which is y squared, equals some arbitrary constant c. That would be our solution when we box it up, but we have this guy to take care of. Now that's kind of a problem on its own. Now I'm going to erase all of this, lift this up, and continue and solving this. Maybe we can even solve completely for y. Let's take a look at that. So I basically erased everything and lifted our last result up, and we're going to attempt to use our initial condition here. Notice here x is equal to 0 and y is equal to 3. So we're going to replace all x's with 0 and all y's with 3, and let's see what happens. Hopefully we can find c. Now let me say at this point, this is our implicit solution. Y is not written completely solved in terms of x. We can possibly get that happening at the end, but let's just hang tight and see if that happens. Now, right, so let's apply our conditions. X is 0, y is 3, and let's see what happens. So we get that term is 0, that term is 0, it's multiplied by x, that term is 3 squared, which is 9, and this is just c. So in fact, right away we get c is equal to 9, perfect. So now we've used our initial condition successfully to actually find c, it's just 9, but now can we solve for y in terms of x completely? Can we turn this implicit solution into an explicit solution? And I believe we can because we have both y squares here and we can isolate them. So let's subtract that 1/3 x cubed to the other side, like this. And if you don't mind, I'm actually simultaneously going to factor out a y squared. So notice here they both have y squared in common. If you factor y squared out, you get x plus 1. Like this, and then finally dividing each side by x plus 1 gives us something. So that cancels. So we get y squared is equal to 9 minus 1/3 x cubed, just like that, all divided by x plus 1. Now if you don't like the fraction within a fraction scenario, that's fine. Multiply top and bottom by the denominator involved, which is just 3. And that'll actually cancel things quite a bit when we don't have a fraction in the fraction scenario. So now we have y squared is equal to, distribute this on the top, we get 27 minus just x squared because the 3's cancel in this case. So let me write it like this. 27 minus x cubed. Good, meant to say. And here, if we want to distribute this, we can. That's fine, I'll distribute it. So we'll get 3x plus 3. Good. And now we have y almost by itself. All we need to do now is just square root. So if we square root, we get y is equal to plus or minus the square root of 27 minus x cubed all over 3x plus 3. Fantastic. What a fantastic problem. I quite like that myself. I thought that was pretty cool. Now I didn't give you too much variety as far as these so-called integrating factor exact equation problems, but I think what I've given you is enough as far as what I'm expecting you to know in the class. I mean, there's a little more we possibly could have said in general, which I kind of want to touch on a little bit, but I don't think it's really worth it. I think just the main concept and idea I've gone over here suffices. And yeah, that's kind of all I want to say as far as exact equations are concerned. I think I've shown enough here. There's only 3 examples, I think, but again, I think it should be enough. So I appreciate you watching the video and taking time to stick through the whole thing. Thanks for watching. I really hope you enjoyed this as much as I did, and I'll see you in the next video. See you then.